Okay, moving on to 12.6. 12, sorry about that one. 12.6, triple integrals still, but now we are going to switch and do in our polar coordinates. I'm sorry. Well, triple integrals in cylindrical coordinates, which uses polar. And we've kind of already seen this when we did this double integrals with polar coordinates. All we're doing is adding that height z to make them cylinders. So shouldn't be too tough of a transition there. Okay, so we're going to go from x, y, z to r theta z. So you guys are used to making that transition from xy to r theta, right? And that's going to be the same. X will be r cosine theta, y will be r sine theta. R is x squared plus y squared, and the tangent of theta is y over x. And here's the good news, z is still just z. Okay, it doesn't change. All right, so we can talk about in cylindrical, where you might have, rectangular, where you might have a point x, y, z. Okay, so actually I'm going to use, I'm going to use red for cylindrical, and I'm going to use blue for rectangular. Okay, so in rectangular coordinates, we would go out a distance x. It could be negative too, but it's just easier if we do it in the first quadrant, the first octant. Okay, then we would go a distance y, and then we would go a distance z, and we would get to our point at x, y, z. Okay, now in our cylindrical, we are going to have r and theta, right? So remember theta, so this same point in cylindrical, we have to measure this distance theta. Okay, and you can see how the tangent of theta would be y over x. And then this distance r, and you can see how x squared plus y squared would equal r squared. And then we would go the distance z to get to the same spot, r theta z. Okay, so there's some examples about converting between the two. So we can do some of these here. Do an example. Plot square root of 2, 3 pi over 4, 2, and convert to rectangular. So those are clearly polar. And then we'll do another one where we'll plot some rectangular and convert to cylindrical. Okay, and again, I'm going to use, just so that I don't forget, I'm going to use blue for my rectangular, and I'm going to use red for my cylindrical. Okay, so let's get some axes set up here. Okay, so I'm going to plot that polar point. So 3 pi over 4, that's actually going to throw me into my negative x's. Okay, so I'll go to 3 pi over 4. 3 pi over 4. Out a distance of square root of 2, and then up a distance of 2. Okay, so there's point P, square root of 2, 3 pi over 4, 2. Okay, so in rectangular, x will be r cosine theta, y will be our sine theta, and z is z. Okay, so our r is square root of 2, cosine 3 pi over 4. So square root of 2, the cosine of 3 pi over 4 is negative root 2 over 2. So I get negative 2 over 2, which is negative 1. Our sine theta is going to be square root of 2 times the sine of 3 pi over 4. So that's going to be square root of 2 times the sine of square root of 2. Oh, I'm sorry, not the sine, times square root of 2 over 2, which is 2 over 2, which is 1. Okay, so my xy coordinates, this would go out to a distance of negative 1. Oops, probably went a little too far there. That would be at 1. Okay, and then z is z, so z is 2. So that same point in rectangular would be negative 1, 1, 2. Okay. All right, moving over to our next example, plot this guy. So x would be 2 square root of 3. Y would be 2. So you go somewhere here in your xy plane. And then z is negative 1. Okay. So there we go. So when we do our conversion, r will be the square root of x squared plus y squared. It's going to be your square root of 2 root 3 squared plus 2 squared. So square root of 12 plus 4. Well, look at that. Square root of 16, which is 4. Theta is going to be the inverse tangent of y over x. So we're going to do the inverse tangent of 2 over 2 root 3. So that's the inverse tangent of 1 over square root 3, or you guys know it better, square root of 3 over 3. Okay, so that's going to be pi over 6. And just make sure you're in the right quadrant, right? Because there are other angles that have that same tangent. The other one would be 7 pi over 6. So just make sure, we are in the first quadrant, so that pi over 6 and then 4 makes sense there. Okay, and then the negative 1. Okay, so that same point in cylindrical would be, z is z. Okay, so it'd be 4 pi over 6, negative 1. Okay, and again in rectangular, that would be 2 root 3 to negative 1. Okay, so we can plot some points now. Next thing would be to take a look at some graphs. So let's do a couple of these. We're going to describe what the graph of r equals 5 would look like. Okay, and we're also going to do 2r squared plus z squared equals 1. Okay. So for r equals 5, that just means regardless of theta, regardless of z, we just have a radius of 5. Okay, so this one would be a cylinder. A circular cylinder, because remember in Calc 3 we talked about you have like parabolic cylinders, okay, with radius 5. And the axis is the z-axis. Okay, so what would that look like? Radius of 5. Okay, and then it would just be a cylinder that basically goes on forever, right? Okay. All right. Then this guy over here, oops, and I missed an r squared here. Okay. You might want to convert this to rectangular to make it a little bit easier for you. So we could do 2, I said x squared or r squared with x squared plus y squared. And you got to think back to chapter 10. With what that's going to look like. Remember, if all the coefficients were the same, this would be a sphere. The fact that they're not the same makes it an ellipsoid, right? Okay, so this is an ellipsoid. And you can think about how it's projected into each plane. In the xy plane, if z were 0, then, well, and go back to even the polar, then 2r squared would equal 1. Our r squared is 1/2. So in the xy plane, we have a circle with a radius of square root. I should just 1 over square root of 2. Okay. You could look at the way that we wrote it in rectangular. If z is 0, then we have 2x squared plus 2y squared equals 1. So x squared plus y squared equals 1/2. Okay, so same thing. In the yz plane, okay, so this would be when x is 0. We would have, now we do want to look at the rectangular one that we have here. Okay, if x is 0, then we have 2y squared plus z squared equals 1. So that'd be 2 over 1/2. I'm sorry, y squared over 1/2 plus z squared equals 1. Okay, so that's an ellipse. And it would go on the z-axis, it would go between -1 and 1. It's centered at the origin, right? And then the y-axis would be going between -1 over root 2. Oops, I already got the negative in there. And 1 over root 2. Okay, your major and your minor axes there, right? And then you'd have the same thing in the xz plane. If y were 0, then we'd have 2x squared plus z squared equals 1. So same thing, it's an ellipse, but now x is between -1 over root 2 and 1 over root 2, and z would be between the -1 and the 1. Okay, so you can kind of draw that little like egg shape there. Let me make some room here. Okay, so in the xy plane, okay, we want that circle with a radius of 1 over the square root of 2. Okay, and then in the other planes, it should make sense. Y is going to be between what it is right now in the xy plane, and so is x, but now z is going to go up to +1 and -1, so that should be actually a little higher than what we got there, 1 and -1, so it's this kind of egg shape. Okay, all right, moving on. Okay, let me get another example here. Forgot where my example was. Okay. Next example. We are going to write in cylindrical an equation that's given to us in rectangular. So we're going to have 3x plus 2y plus z equals 6. And we're going to do another one too. We're going to do b also. I think this is number 10 in the textbook. -x squared minus y squared plus z squared equals 1. Okay. And again, you guys, I would encourage you to graph these so that you can see what they look like. But you're just going to use your conversion. So in place of x, right, I'm going to put, and that's not squared, sorry. It's just a plane, okay? So in place of x, I'm going to put r cosine theta. In place of y, I'm going to put r sine theta. And in place of z equals 6. Okay, a lot of times we might like rearrange that. We might solve it for z. So z equals 6 minus 3r cosine theta minus 2r sine theta. We might even factor an r out. I think they do that in the book. Doesn't really matter, but it's as straightforward as that. Okay, this one's a little bit different. You could go ahead and swap out the x's and the y's and simplify, but you can also recognize that that's negative x squared plus y squared plus z squared equals 1. So that'd be negative r squared plus z squared equals 1, or z squared is 1 plus r squared. Okay, that's it. All right. Then, and you didn't even have to like graph those, so just real quick practice with going between them. Okay, we're kind of doing a bunch of examples here. I'm going to get to a little bit of a proof here in a second, but one more example. We're going to sketch, and this is number 12 in the textbook, I believe. Theta is between 0 and pi over 2, and r is between, oh, actually it's z, sorry. Okay, z is between r and 2. Okay. Before we get too far with this, I want you guys to think about what r equals z looks like. Okay, because that's something that comes up a lot. So graphically, you can think about it. If remember, r is measured out from the origin, okay, in the xy plane. So you would think about wherever r is, z is the same distance up, okay? And so I could be like here, up, okay? So think about that for a second. However far out I go from the origin, so if I'm at the origin, it's 0, okay? But if I go out 2, I go up 2. If I go out 4, I go up 4. If I go out 6, I go up 6, okay? Think about that for a second. All of the lines through the origin with a slope of 1 like that, that's going to make a cone. Okay, that would be a cone at 0, 0, 0, because remember, r is always positive, okay, and with that slope of 1 to 1. Okay, that's a pretty common figure to see in these excuse me, these types of problems. Okay, and so that's a surface. R equals z is a surface. Okay, so that's going to help you a lot here. So let me erase this kind of messy sketch I've got here. Okay, but I'm gonna, this is r equals z. Okay, so if theta is between 0 and pi over 2, that means that we are only in, oops, I made them all solid here. Kind of don't like doing that, like the dashed. Hold on, sorry. Okay, come on. Okay, so if theta is between 0 and pi over 2, then we are only, here's theta equals 0, here's theta equals pi over 2. We're only in that range there. Okay, so that'd be the first octant and the fifth octant, I think, if I'm numbering my octants correctly. But theta is between 0 and pi over 2, and then r is between z. Okay, so we'd be between r equals z, which is that cone, and z equals 2, which would be a plane. Okay, so think about like the plane up here. So we're a quarter of a cone that is bounded by that plane. So let me draw a little bit of a better sketch here from kind of a different viewpoint. Okay, so we'd want to think about this cone. I'm going to draw that a little higher up. My fault. Let me fix it. Okay. Okay, there we go. And so you can kind of like picture the edge of the cone there. Okay, and it comes into that corner. This would be the projection onto the axis. Okay, it's not part of the figure, but it's just what it would look like with that projection. Okay, so it's a quarter of a cone, only in that first octant there. Okay. All right, now we're going to get into a little bit of the proofy stuff. Okay, because now we're going to get ready to do the integrals. All right, integrals, our favorite. Okay, so we are going to use cylindrical when the region D, okay, can best be described with polar coordinates. Okay, so I'm going to get a little sketch going here for you. This is a good one. I like this sketch. Okay, and then do something like that's pretty good. Okay. So we've got this figure out in space. Okay, and I can project it down onto my axis. Okay, that's what it looks like projected. Okay, so what we've got here is, first of all, let's get the angles first. Okay, so first of all, we have this theta 1. Okay, and we're going to call that alpha. And then we can also, I'm going to draw that kind of dashed, go out to the other theta. That's theta 2 is going to be, you guessed it, beta. Okay. And again, this is that projection of the base. Next, we're going to look at this piece right here, which would be R1, which is some function, they're going to call it H1 in your book, of theta. Okay. Here it looks like it's definitely just R equals a constant, but it could really be any polar graph. Okay. And those can get kind of scary sometimes, but they're also kind of fun. Okay. And then here would be our other R2 is some other function of theta. Okay. And I guess I'm going to erase those arrows because they don't necessarily have to be a constant. Just kind of what those arrows would be showing. Okay, some polar graph. Okay, so those arrows are just kind of pointing to the piece of it. Okay, so there's your projection. All right, and then we look at that figure, and it's got its z-bounds. Okay, so the bottom here, which looks to be maybe flat, but it could have a curve to it. Okay, or a slant. That one would be z1 equals some function of x and y. Okay, which again will convert it to r and theta. And then we're going to have the top z2 is some function of x and y. Okay. All right. So, and again, we're going to call this piece D. Okay. And this entire shape here, this entire volume, E. Okay, it's just what they do in the book. So let's write some of this stuff out. Okay, E is all x, y, z, okay, such that x and y exist in D, and u1 of xy is less than or equal to z is less than or equal to u2 of xy. Okay. Now, though, if D is r and theta, okay, such that alpha is between, or sorry, theta is between alpha and beta, and r is between h1 of theta and h2 of theta. Okay, that's when we're going to want to switch to polar. Okay, is when that D, right? I don't have to change anything up here in E. Okay, that's all true. All the x, y, z ordered pairs, such that x, y is in D, but D is best described using polar coordinates. So we're going to want to use them, okay, and we're going to use them in our integral, okay? So some of this is going to look familiar from 12.5, your triple integral over E of f x, y, z dv, okay, is your triple integral, or sorry, double integral over D times your integral u1 of xy, u2 of xy, f xyz dz, and then dA. Okay, that's what it looked like when we just stuck with rectangular. Okay, so we're just swapping out that dA for our dr d theta, and we know that we have to throw in the extra r, because remember we have that extra r in there. So we're going to do that double integral. Instead of going between x and y now, we're doing theta and r. Okay, now if h1 and h2 are constants, the order is not going to matter. But if h1 and h2 are actually functions with theta in them, then that's got to be our integral. Okay. Okay. And then we're going to switch our function to be in terms, instead of x, y, and z, it's going to be in terms of r cosine theta, r sine theta, and z. Okay. And then we're going to have to throw in the extra r. Oops, you know what? I don't want that bracket there. I guess I don't mind it there. Okay, I'll leave it. dz. Okay, and then dr d theta. Okay, so again, if you look here, and I'm going to use like my highlighter, I think, instead of okay, so we didn't change this. Those stayed the same. Okay, we swapped out the x for r cosine theta. We swapped out the y for r sine theta, and z stayed the same. Okay, we still have the dz, and then we swapped out dA for dr d theta with the r. Okay, so we've just made that complete transformation, or conversion, I guess I should say, from rectangular coordinates in our integral to the polar coordinates. Okay, super fun stuff. All right, so let's do some integrals now, because this is what we're all here for, right? Triple integrals and cylindrical coordinates doesn't get much better until the next chapter when we get to spherical. Okay, or next section, I should say. All right, let's start with a nice, easy example. This one's number 16 in the book. Okay, so they want the integral from 0 to 2 integral from 0 to 2 pi, integral from 0 to r of r dz d theta dr. Okay, now a couple things here. They want us to sketch it and then integrate it. Okay, notice there's no function in here, right? That r is from working in polar coordinates. So f of x, y, z is just 1, and that means that we're finding the volume. Okay, so let's start to sketch it. Or I shouldn't even say f of x, y, z, but also f of r theta z too. Okay. All right, so pick apart our integral here. Z is between 0 and r. There's that z equals r again, right? That cone that we're used to, but now we're under the cone, right? Between 0 and the cone. Theta is between 0 and 2 pi, and r is between 0 and 2. So when we sketch this, okay, so again, it helps if you think about your base first, where r is between 0 and 2, so r is that circle, and theta goes all the way from 0 to 2 pi. So we just have a circle, right? R and theta give us a circle with a radius of 2. Okay, now z is between 0 and r. So if you can think about, on top of that, having cone, I'll use a different color. I always forget that I can just use a different color. Okay, so we got our cone. Okay, and that is going to be between 0 and r. Okay, so whatever r is, that will give us how high up we are on the cone. So the highest you're going to get on that cone is 2, right? We're between 0 and r, but the biggest that r is going to get is 2. So this cone will kind of go to the edges. Okay, think, if you will, about like it's a cylindrical with this little conical piece drilled out of it. Okay, can you kind of picture that? Sometimes it helps if you just kind of shade the sides a little bit. Maybe that doesn't help as much, but okay. Kind of like that shape, but knowing that inside it comes to a point. Okay. All right. So that's the tough part, right? That integral, not bad at all. We can do that integral, no problem. Okay, so we want to integrate with respect to z first. Okay, so we will have your integral from 0 to 2, integral from 0 to 2 pi. We're going to have rz evaluated from z equals 0 to z equals r. And then we'll have our d theta dr. So that's our integral from 0 to 2, 0 to 2 pi, where you're going to have just r squared. Okay. Now integrate that with respect to theta. Okay, so again, the theta being 0 doesn't affect anything. So we're going to have 2 pi r squared. Okay, and then the last thing we do is we integrate with respect to r. So 2 pi r cubed over 3 from r equals 0 to r equals 2. Another 0 in there makes it easy for us, so we'll have 16 pi over 3. All right, fun stuff. Okay. Let me see here. I have a lot of examples here. I'll do another one. Let's see. So the one that we just did was 16. The next one, let's see here. What is the next one that I want to do? Maybe I'll do number 20. So in number 20, we're going to evaluate triple integral over e of x dv, where e is enclosed by the planes z equals 0 and z equals x plus y plus 5, and the cylinders, so these are planes, which we know, the cylinders x squared plus y squared equals 4, and x squared plus y squared equals 9. And that should make sense that those are cylinders, right? Those are circular cylinders even. Okay, so again, we might want to kind of sketch this first, especially because there's a lot going on. So, so those cylinders are kind of easy to draw. Actually easy to imagine too, okay? So x squared plus y squared equals 4. That will be r equals 2, right? R squared equals 4, so r equals 2. And this one would be r equals 3. So just swap out your x squared plus y squared for r squared. R squared equals 9, so r is 3. So we want to go between 2 and 3. Okay, so we'd have this, r equals 2. So imagine that, again, just being a cross-section of a cylinder that goes straight up and down from there. And then r equals 3. So we're in this ring. Your book will call it an annular region. Okay. And then we're cut off, right? So you can imagine those cylinders going straight up and down. In fact, maybe I'll use my highlighter. I kind of like using that for the dashed lines. Imagine those cylinders just going straight up. I missed a piece in that third quadrant there. In the fourth quadrant. Let me fix that for you quick. Okay, so we've got these like cylindrical Chromebook's being really slow right now. Okay, and you can kind of picture it going all the way around. Okay, so we're in between those two cylinders. We're being chopped off by z equals 0. So that's pretty easy. That's just your xy plane. Okay, and then also this plane, z equals x plus y plus 5. So you can get some points there. If x is 0 and y is 0, then z is 5. If z is 0 and x is 0, then y is negative 5. And then what's the other one? X would be negative 5 too. Y is negative 5, x is negative 5. Okay, so we've got this plane. If you can imagine the plane that would go through those 3 points, it's just coming right down and slicing through that guy. Okay, slicing through that tube. Okay, so what you might see here, I'm going to kind of try to draw the plane a little bit. Oops. Okay, that's just that triangular region of the plane that we can draw, but imagine it going on forever, and we're just coming through and slicing. So what this might look like from kind of a different viewpoint okay, because it is kind of like that negative x and y where it's slicing down. And that should be more straight up and down. Okay, almost like that. Okay, where this part is higher and this part is lower. Okay, that's about what the shape looks like. Okay, so now we can get our limits here. Okay, so clearly theta would be between 0 and 2 pi. Okay, r is between 2 and 3. And then z is between 0 and 5 plus x plus y. Okay, now the thing with this is that we can have the x's and the y's, right? So that's a real easy switch. 5 plus r cosine theta plus r sine theta, or just r cosine theta plus sine theta, like that. Okay, there we go. All right, so now go back to our integral, and we're just going to swap everything that we need out of there. Okay, so we will have the integral from 0 to 2 pi, 2 to 3, 0 to 5 plus r cosine theta plus sine theta. Okay, and which means that we're going to have at the end dz, dr, d theta. Don't forget your extra r. Okay, and then our function was x, so now it's got to be r cosine theta. Okay, so I'm actually going to, we're going to switch that x to be r cosine theta, and we already have this r here. So we're just going to write r squared cosine theta. And there we go. Okay, that is your integral. It gets a little bit messy. I shouldn't say messy. Just a lot of sines and cosines going on there, because when you integrate first with respect to z, you're throwing those in there right away. Okay, so just be real careful with those. I'm not going to go through and do that entire integral because I think you guys can probably handle it. It's the setup that's the hardest part. So just make sure. I say that and then I feel bad just leaving it. So maybe this one I'll go through. You know what? I'm going to leave it. I'm going to let you guys do this one. I am just going to caution that when you do 0 to 2 pi and then 2 to 3, okay, integrate first with respect to z. So your first integration, we're just going to tack on a z there. We're going to evaluate it from z equals 0 to z equals that upper bound, so the 0 won't matter. So we will just have r squared cosine theta, and then 5 plus r cosine theta plus sine theta, dr d theta. Okay, so that should get you started. This is probably going to be something that you will expand before you do your integral with respect to r. Okay, but you will eventually get there, and the final answer is 65 pi over 4. Okay, so I would encourage you to try that for yourself. Make sure you can get that final answer. If you're having a hard time getting it, just let me know, and then I'll make another video that walks you through it. Okay, let's do another one here. This one is number 25 in your book. Okay, and then we'll just talk about one more thing before we're done. Okay. we want for this one, the volume of the region bounded by the paraboloids z equals x squared plus y squared. Z equals 36 minus 3x squared minus 3y squared. And oh wait, is that it? I'm getting ahead of myself. Okay, and then find the centroid. Okay, so this is actually the last thing we'll do. Which is your center of mass. Okay, since we would assume that the centroid is the center of mass when density is 1. Or constant, I guess I should say. All right, so first we're going to look at those paraboloids. Okay, and remember the shape of a paraboloid is this. Okay, so our first one, we have z equals x squared plus y squared. So if you think about that, like how these paraboloids look, right? If x were 0, we just have z equals y squared in your yz plane. Okay, so your parabola that opens up, your parabola opens, let me think about this, yeah, towards z, right? Sorry, this one. So if x were 0 on the yz plane, we just have z equals y squared, which is, in your zy plane, it would look like this. Okay, and then we have something similar going on in the xz plane. So this parabola looks like, or this paraboloid looks like that. Okay, and you can see in polar that would just be z equals r squared. Okay, then our other paraboloid, we have z equals 36 minus 3x squared minus y squared. Okay, that one's a little bit tougher to kind of figure out, but you can still do it. It's just that 36 kind of throws you off, doesn't it? Like if x were 0, then we'd have z equals 36 minus y squared. So 36 minus y squared, that's just a parabola opens down, but it's way up there with a y-intercept of 36. Okay, so that opens down. Okay, and then if we make y 0, we have z equals 36 minus 3x squared, so that's another parabola just with a different stretch factor. Okay, be a little bit skinnier. Okay, so it's kind of that shape to it. Okay, and so now when we put them together, we have this blue paraboloid that opens up. We have this purple paraboloid that opens down. Oops, and I gotta switch that purple one to polar for you too. Okay, so this purple one that opens down. Maybe I kind of got a little weird shape to it over there. Just a second. Roughly. Okay. And again, that purple one goes up to 36. Okay. And then what's going to happen is they will intersect kind of along this little ridge here. It's going to be kind of like a flying saucer shape to it, right? Let's get some of the shading in there maybe for you. Okay. Okay, if you can imagine that. Kind of, right? Okay, so here's a couple things that we can figure out by looking at that. Oh, and I got to go back to this one. Remember that, what do we want to do there for that to be polar? Oh, you know what? This is going to make I forgot a 3 there. It would be okay if we didn't have the 3 there. We could still do it, but this is just a little bit easier. So that means that my stretch factor on there was maybe a little bit off. But this would be then z equals 36 minus 3r squared. Okay, there we go. All right, I'm just checking my work here and make sure that I got everything. Okay, so we can tell right away a couple things. First of all, we can tell that r is between 0 and something. And that something we need is whatever that radius is where they intersect. Okay. So we have to figure that out. Okay, but otherwise then, theta all the way around, so 0 to 2 pi. Okay, and then z is between, let's see, the lower one. So if we connect our roof to our floor, right, the lower one is that blue parabola that opens up, and the upper one is that purple parabola that opens down. Okay, so now all we need to do is figure out where these intersect. Okay, and it's not too bad at all. They intersect, right? Obviously, where these two equations equal each other. So where r squared equals 36 minus 3r squared. Okay, so then we'd have 4r squared equals 36. Getting a little glitchy here. So then r squared is 9, and r is 3. Okay. So we know that's going to be 3. Okay, so then our last step, again, setting up the integral. We did all the hard stuff now. So our integral, we can go 0 to 2 pi, 0 to 3. And again, we could switch those if we wanted to. Okay, and then z goes from r squared to 36 minus 3r squared. Okay, and we're finding the volume of a region, so that means our function is 1. And then we've got the r dz dr d theta. So we're going to go through and do that integral. Again, that's something I'll just leave you to do on your own. This one is not, the one before this was a little bit more involved. This one is not too bad at all. And you can do it yourself and just check that you get 162 pi. Okay, and then the one additional thing on there is we want to find the centroid. So we're going to find, again, so remember that x bar, y bar, z bar would be the moment about, let me get this here, yz over the mass. I'm sorry. Yeah, over the mass, I guess. Okay. The moment, sorry, I did think of for a second because I was just finished teaching the earlier class that was just doing 12.2 today. So I could get my brain around back to 12.5. And this would be xy over m. Okay. So now the good thing is that the mass, remember, we're talking about if the volume is if the density is constant, the mass is just some constant times the volume. So 162 pi, I think in your book they use K. Okay, just represent whatever the constant volume, I keep saying volume, density is. So there's your mass, okay? And then additionally, if I look at the graph, that symmetry that we have there means that the moment of that guy around YZ is 0, and the moment around xz is 0. Okay, so let me go back up here. Your tendency to revolve around the YZ plane would be nothing because we're centered there. Okay, and your tendency to revolve around the XZ plane would also be nothing because we're centered there. Okay, it would be the big tendency here would be to revolve around the XY plane. Okay, so that's what we need to find. Is we need the only thing that we really need is the moment around XY. Okay, and then remember then that is the integral around z times your density. Okay, and then r dz dr d theta. Okay, so again, if you want to go back into, was it section 12.5 or 12.4 that we did the moments there? Yeah, if you want to look back in section 12.5 to kind of refresh your memory on some of those, you might want to do that. But just remember, in general, the moment around xy is your triple integral of 0 dv. Okay, so that's exactly what we're doing right now. So z is z, rho is this constant, okay? And then dv, we're not doing dx, dy, dz, we're doing r, dz, dr, d theta, okay? So for this one, we would do, again, using the correct limits, 0 to 2 pi, 0 to 3, r squared to 36 minus r squared, or sorry, 3r squared, z, k, r, dz, dr, d theta. Okay, now, and again, this is another one I'm going to leave that for you to do. It gets to some bigger numbers, but the integration itself is not difficult. You should get 2,430 pi times k. Okay, which means that when we find that moment around xy over m, the k's cancel out. First of all, the other ones are going to be 0, right? 0, 0. This guy, let me get it here. Good thing we're almost done because this is being really slow. We would do 2,430 pi k over 162 pi k. So both of those cancel out, and it actually ends up, that's 15. Okay, so your final answer is 0, 0, 15. Okay, there you go. So a couple of things here, again, work through it on your own. Make sure you understand why these two moments are 0. Basically, your YZ plane just goes right through the centroid, right? You guys could, I mean, without even knowing this, you guys could tell me the center of mass here, well, X would have to be 0 and Y would have to be 0 because it's circular around it, okay? It just makes sense that X bar is 0, Y bar is 0, and Z bar is going to be higher up, okay? And in fact, we found the Z bar was 15. This is not a perfectly, we go between 36 and 0 here. And this ridge is not right in the middle at 18. Okay, so that center mass isn't at 18, but it's at 15. Okay, and that should make some sense there. That whole center of mass there is at these coordinates. Okay, I would encourage you too, if you're not understanding why those are 0, try to do the integration. Okay, try to do these integrals with an x here instead of a z, or with a y there instead of a z, and see why it's going to be 0. Okay, all right, and that's it for 12.6, folks.